Good morning, everybody. So I will present in this talk the most recent results from the HES experiment. So I should make it clear that I belong to the HES collaboration as a theoretician. So collaboration thought it was a good idea that theoretician could present our results. I hope that it is. So I can maybe not answer all technical questions about observations we talk about. But I could maybe answer some questions about what I want to talk about. So as probably most of you know, the HES is a system of 4 atmospheric June2 telescopes. So we have had already a talk about magic experiment. So I won't recall the basic principles of June2 detection. It's located in Namibia, in the southern atmosphere, and its originality is this stereoscopic arrangement with 4 telescopes, which gives a precise view of the showers in 3 dimensions, which helps a lot to discriminate them from the background and to identify the precise direction of the shower, so the origin of the vision. So thanks to this setup, we can reach a very good sensitivity of theoretically 1% crab at 5 sigma in 25 hours. That was the nominal sensitivity. To be honest, and you will see later, the sensitivity has somewhat degraded in the time, and now it's more 100 hours to reach the sensitivity. The energy threshold is about 100 GeV, and the field of view is 5 degrees on the angular resolution, about 1 meter. So the location is an ideal one to observe southern objects like the galactic centers, the galactic plane, some bright blazars and radio galaxies, as you see. But of course, this is some northern objects with blazars.
So what's causing the degradation?
It's basically the mirrors are covered with dust, and there is some edging of the infrastructure. There are some problems with some drawers, and so that's like it. So maybe one of the major achievements of the HES experiment is this survey of the galactic plane that has been regularly performed since the beginning of the instrument, and which has detected a number of sources, and all of which are not yet identified. You can see some of them are very clearly associated with known objects, like the galactic centers. We talk about some of them, supernova remnants, binaries, and pulsar, binary pulsar. But some of them are yet unknown, so I won't take more about this unidentified object. They may be associated with the stellar association and wind from massive stars interacting with the interstellar medium, but there is nothing certain in the identification. So, starting with galactic objects, I will talk about recent detection of supernova remnants. So historically, it was one of the goals of the telescopes, June2 telescopes, to identify precisely the origin of cosmic rays and to prove that the cosmic rays were really generated and accelerated in the shocks produced by supernova explosions. And for this goal, the hope was to detect the gamma ray emission from the enhanced cosmic ray density around these objects. So that is been partly fulfilled with the detection indeed of supernova remnants. The first one was published in 2004, RxJ 7037. And it shows indeed that supernova remnants can accelerate particles up to 100 TeV. Although the origin of the emitting particles is yet not clear, it could be associated with harmonic processes and the formation of pions with proton-proton collisions, giving gamma rays, or with inverse compton from very high energy electrons accelerated in the same shock. So this is still a matter of debate, you will see, but it's certainly true that that efficient acceleration takes place in the shocks around this supernova remnant. So the object I will talk about is SN1006, which which is a known supernova remnant associated with an historical supernova, which is related in ancient Chinese chronicles, like the Prague Nebula. It's supernova 1A type. It's an extended shell with 30 minutes diameter. It's relatively in a clean environment. It's out of the galactic plane at a distance of 2.2 kiloparsecs. And there is relatively few material around, which means, which makes it a very clean object to study the physics of the expansion of the supernova. But there are some stars around that make the observation difficult, and it must be understood that, that for atmospheric Cherenkov telescopes there is a huge background of hadronic showers, even gamma ray showers. So the detection of extended objects is a very difficult task, and it requires very careful data analysis. So it has been imaged in X-rays. Here you have a composite image obtained by XMM. And you see that that's a low energy band of XMM. You see some rather spherical structure, which is interpreted as thermal X-rays emitting from material heated by the shock. But at high energy, it's very different because you have these two zones of emission concentrated around poles. So you have the northeast and the southwest winds. And that has been interpreted as non-thermal X-ray emission from synchrotron radiation from electrons accelerated through the shocks. And it indicates that the efficiency of acceleration depends on the location of the shell. And that has been interpreted by a magnetic global structure with a dipolar field with a more efficient acceleration when the magnetic field is parallel to the normal of the shock. It's known in the shock acceleration theory that the acceleration is most efficient in this configuration. So at TeV, the detection the detection has been claimed by Kangaroo 1 and confirmed by Kangaroo 2 at a few 10 to the minus 12 photons per centimeter per second, which is given by this curve here. And it was one of the first targets of Hess, of course. But unfortunately, after 24 hours of exposure, Hess could only set upper limits of detections, which were well below the claimed detection by Kangaroo. But there was some hint of a possible signal, but not enough to measure a process. So probably there was something wrong in the Kangaroo detection, because of course these kind of objects are not expected to be time variable. Not at this time. So we had more observation time until we reached more than 100 hours exposure. And it has been finally detected at a flux comparable to the 1% of the Prague flux. So as I said at the beginning, we need now more than 100 hours to detect that. And we see an image which is very close to what we observe in high energy X-rays. So here is a comparison between, so that's the significant histogram. You see all these pixels are significant with the background. And it's very clearly associated with the XMM image. When you smooth the X-ray image with the resolution of Hess, you can see a very, very close picture of the. So it's most probably produced by the same particles, but there are still two possibilities, as I said, and it's not clear for this object as well as for the others. You can invoke tectonic process when basically the emission is produced by inverse Compton on the 2.7K cosmological background, which is the dominant source of energy density, radiation energy density in the supernova remnants. And so you can easily constrain the synchrotron spectrum and reduce the magnetic field from the ratio of the energy density of magnetic field in the cosmic background. And it requires values that are reasonable of 30 microgauss. Or it can be explained as well with hadronic processes, with the collision of protons, of relativistic protons, with interstellar matter, giving pions and giving chimeras. So in this case, you will constrain the density of protons, and it requires about 20% of the total energy stored as cosmic rays, which is also not impossible. So both explanations are possible, and if you look at the detailed spectra, the leptonic models tend to be too soft with respect to observations, and the hadronic models tends to be too hard. So it may be that you have in fact a mixture of two. It's not exclusive. In this case, the energetic content will be dominated by hadrons because the leptons radiate much more than hadrons for the same energy. So another object I will talk about is the binary pulsar PSRB 1259. It's a well-known binary pulsar associated with a massive B2E star, which emits a strong decretion flow in the equatorial disk. And it was known that the orbit was very elliptic and that the pulsar will cross, will get very close to the star around the periastron. So it was observed around the periastron in 2004 by Hess, and it was indeed detected with a complex light curve showing two maxima, which has been interpreted as the passage of orbit through the wind, with two crossing around the star. And probably the interaction of the pulsar wind with the material of the wind produce a shock and accelerate particles and increase the radiation. So a new passage to the periastron was expected for July 2007. So you see here the reconstructed orbit as a function of what's called the true anomaly, that is the angle with respect to the axis going to the periastron. And surprisingly, a maximum has been detected, but not at the right time. It was more than 50 days before the theoretical passage to the periastron. So reality is not as simple as what it was expected, as usual. So the maximum was around here. So how can we interpret that? Probably it's more complex than a simple interaction with the disk. There is maybe a complex environment around the star and changing environment, and the interaction maximum interaction can take place at various locations in the orbit.
So the direction of the observer was from below there?
I think it's not indicated. I think that's I don't remember, sorry. I think it was indicated as well. So another kind of object close to this, maybe close to this one, but it's in dispute, is the so-called gamma ray binaries that have been seen by Egret and confirmed by Fermi, and seen for LS 5039 by Hess, and there is a similar object LS 151 seen by Magic at TeV, and we already heard about this object. And again, the TeV emission has been seen in this object with a clear orbital modulation. But the interpretation of this object is still a matter of dispute. It can be interpreted as a accreting microquasar with very high energy emission from the jet, analog to the blazar we talked about in a few minutes. Or, following the interpretation of Dudus in 2006, it can be closer to the previous object, that is a pulsar wind interacting with the wind of the massive star, and acceleration could take place at the shock between the two magnetic structures. So there has been detection of a cometary tail in radio observations that seems to support more this interpretation, but some other people in the room will have another interpretation. So it's fair to say that it's still open. And there is a very clear spectral change between the superior and the inferior conjunction. The dip here can be interpreted by the absorption of gamma rays by the star of the light during pair production. But in fact, simple pair prediction estimates predict a completely vanishing flux at the superior conjunction when the optical depth is the maximum, whereas we see still some emission at this point. So either the emission takes place farther away, which gives a lower photon density of the star, or there is an influence of the pair cascade that could produce a pair halo, explaining part of the dish. So now turning to the extragalactic TV sky, where it's active, it's dominated by AGNs. In fact, the only up to now the only objects we can see are AGNs. So as you see, AGNs are interpreted by the presence of supermassive black hole creating material, interstellar material, and giving rise to, in some cases, powerful relativistic jets. And there are all zoology of AGNs following the location of the jet with respect to the line of sight. If the jet is seen directly at small angle, you have the so-called blazars, whereas the radio galaxies are thought to be objects with a misdirected jet, with two kinds of morphology, either FR1 that are associated with blazars called BLAC, or FR2 that are thought to be associated with flat spectrum radio quasars. So it has been claimed by the Italian group, that there was a sequence of spectra extending from the high energy peak BLAC to flat spectrum radio quasar, and with a systematic decrease of the peak energy. So these spectra are interpreted most often with the SSE model, with the first component originating from synchrotron radiation and second component originating from inverse Compton process. The inverse Compton can take place on synchrotron photons themselves, within the SSE process, or on external photons from the accretion disk or lines or so I won't enter all the details, but this sequence predicts that the highest energy should be detected from high energy BLACs, which has been mainly true, but now we start to see other type of objects, and we have seen that with the magic torch. So here is a list of the AGNs seen by Hess. It's 12 AGNs published. There are some still unpublished and still unstudied. So it's about 1/2 of the total number of TV AGNs, because we miss all the northern hemisphere. And on these 12 AGNs, 9 have been detected by Hess, and some of them recently, as we see. So the 2007 detections were published in 2008, and Centaurus has we talked about it, have just been published. So it's continuous. We discover continuously new AGNs thanks to better and better exposure time. So most of them are indeed high energy BLACs, but two, you see the two famous radio galaxies. So M87 we talked about yesterday, and a new one I will talk about Centaurus K. So I think one of the most extraordinary observations was that of PKS 2155 minus 304. Observed in July 2006, and it has shown an extraordinary flare on the night of the 27th to the 20th of July. The flux reached 20 times the flux of Pratt, which is 50 times the average flux of these objects, and 100 times the minimal flux observed, with a doubling time scale, very short doubling time scale of a few minutes for the shortest flares. And if you look at that, you may think it's a gamma burst, but no, it's a blazar, a flare of a blazar. So if you believe the estimate of the mass of the supermassive black hole deduced from the mass of the galaxy, it gives a mass of 10 to the 9 solar masses, and it gives a very high minimal Doppler factor for a reason of causality, more than 100, but maybe this determination is not quite precise, so maybe a lower mass, because there is some dispersion in the calibration of the mass of the black holes. But indeed, it shows a very huge Lorentz factor necessary to explain this observation. So I just mentioned, I won't talk much about it, but that this observation has been used as other flares to put constraints on a possible variation of the velocity of light following the energy. So that's a prediction of some quantum gravity theory that the highest energy photons should have a smaller velocity than light. And this could give an observable delay between the low energy part and the high energy part of the spectrum. This delay has not been observed. If we had observed it, we wouldn't have proven that the velocity of light is varying, because it could be due to astrophysical effects. But if it's all simultaneous, it's very unlikely that, that astrophysical effects will compensate the variation. So it gives upper limits which are the most stringent ever obtained by this method. So the first flare was observed without other instruments, but it triggered immediately the observation, a coordinated campaign with a TO observation of Chandra. Unfortunately, the night after, the 2 nights after, there was a second flare, not as high as the first one, but still very, very important. And this flare was observed simultaneously with Chandra and with optical pulses. And this gives a beautiful set of data, simultaneous data, which is very rare for this kind of event. And it's very interesting to look at this data. So that's the overall spectral energy distribution that you can observe with the highest points here observed during the flare, that's the quiescent state. And that's, I think, the minimal and the maximal value of so you see that the variability of TeV is correlated by, you will see that it's correlated, but it's much larger than the variability in this phase. And you see this dramatic increase of TeV fields. And the so-called Compton dominance, that is the ratio of luminosity of the Compton peak to the synchrotron peak, is much larger than 1 in this case for the highest point, which is 5. So it can be that there is some other component that the synchrotron process, because the SSA process predicts naturally around maximal ratio of around 1, unless you enter the Compton catastrophe, where the cooling becomes catastrophic with respect to synchrotron cooling. So it may be that there is another source of photon, external photon, or it may be also that you are at some time in the condition of catastrophic cooling, because it's observed only during the flare, so maybe it's the impulsive release of energy that gives very quick cooling, and you get back to the normal condition, more normal condition. So if you look at the TeV flux as a function of the X-ray flux, you see that during the flare there is a dependence very close to the cubic one, with the TeV flux varying as the X-ray flux to the power of 3. It's difficult to, almost impossible to explain this kind of dependence in simple one-zone SSE models. So you have to invoke more complicated models to explain. So another observation you talked about in the first part of the session is a coordinate campaign just after the launching of Fermi between Hess, Fermi, X-ray satellites, and ATOM, which is an optical telescope on the Hess site devoted to the monitoring and to multi-wavelength observation. So you have already seen the spectrum, but that's the result, which is very, very interesting, because you see that the spectrum is not a simple power law. You need at least 2 breaks to explain the results. So you can fit it with a single zone SSE model with 2 breaks, and that's a general feature that you can use the one zone model to fit overall SED, but usually there are great difficulty to explain all the variability on the correlation. That's why the variability studies are very unavailable to put constraints on the model. And it's not enough to say, okay, I can fit that. That's usually what we do in Hess papers. But it's just to have an order of magnitude of the physical parameters. But when you look more carefully at the data, it's not enough to use this kind of quantum model. So if you look at the correlation, for example, it's much less clear than for the big flares, in the standard flare. You see that the Hess-like curve is quite different from the Fermi one, which is almost constant, and not obviously correlated. In fact, there is no measurable correlation between the X-rays and the TDP data. But there may be some correlation with the optical data. If you look at the correlation, you have a hint of correlation between TV and optical, but not between TV and X-ray. And another result is there is a sign of anti-correlation between the GeV spectral index and the X-ray flux. That means that when the flux is lower, the GeV spectrum is harder. So of course, there is much work for the theoretician to explain all this complicated behavior. Just to make some advertising of work done with the students. There's a kind of model there are many proposals, and that's a model we have proposed with a continuous jet, which is in fact based on the two-flow model. That is a continuous jet filled by an electron-positron plasma, surrounded by the magnetized jet from an accretion disk. And that the electron-positron are responsible for the high energy emission, and it's continuously filled with this electron-positron plasma. And it's enough to do some small variation of the initial injection of electron-positron. And the small variation are amplified by the electron-positron percussion process, so gamma-gamma interaction. And you can explain this kind of flare. You see the light curves can be rather well reproduced. Of course, you have to adjust some fluctuation of the initial injection. But it's like weather, it's not very predictable from the beginning. You have to assume some variation of something to explain the observation. So now turning to the radio galaxies, we heard already with the magic with Robert Wagner's talk for magic that the M87 has been observed by TV telescopes. It has been observed first by EGRAD, then confirmed by Hess, and Veritas and Magic at CMB. So it's a powerful radio galaxy at the center of the Virgo cluster, and it's well done because it has a prominent jet visible in optical light, in radio, here in X-rays. And it has shown strong variability detected by Hess in 2006, and the flares have been detected in 2005, just at the same time as a flare of a component which is not in the core, which is HST1, which has been seen flaring in X-rays through the years before 2005. And also by the Space Telescope in optical, you see very conspicuous flare here in the optical. And so it could be, it has been interpreted that as a possibility that the TV emission could originate from this node, HST1. So the joint observation with Magic and Veritas has been performed in 2008, and it's not the Hess point where rather quite, but Magic and Veritas have detected flares around, but the overall covering is very good. But here it's the opposite of the 2005 observation. That is, the HST1 is in a low state, and the core was active during this observation. So things are, again, not so simple, and it discovers the origin of TV emission from HST1. It's more compatible with origin. So another famous radio galaxy, which is the closest one, in fact, is Centaurus L, which has a complex structure of elliptical galaxy, a dust strain, a radio jet, seen also in X-rays. And it has been detected recently by Hess after more than 100 hours of observation, again, at 1% of crab, with no hint of variability. And the flux seems to be compatible with a great measurements, which is 90s, in the extrapolation of the vector. So this leaves the question of the origin of the peak here seen in around 100 keV, which has been interpreted either in gas quantum or synchrotron. It may be an overall quantum hub, or it may be another component. It's not yet clear with the data. And as there is no variability, it's difficult to correlate. So the fact that we see radio galaxies puts very severe constraints on the model, because if you take the high Lorentz factors that are deduced, like in PKS 2150 from the observation of lasers, it should be impossible to detect radio galaxies, because with this Lorentz factor and with this large angle around 30 degrees, the emission should be completely deboosted with an inverse boosting Doppler factor, and that should be completely invisible. So it requires a more complex structure with at least two, maybe four continuous pattern of Doppler factors that can explain that you can see the radio galaxy with a large angle, and there can be a mass beam component in blazars. But even that is complicated because the number of blazars, detected blazars, here, the number of detected blazars is too large if you just take a simple Doppler boosting model with this high Lorentz factor. You should have a very tiny fraction of blazars seen, which is not the case because Hess has detected a number of closed wavelengths. So there are, I won't discuss all this model, there are a number of proposals. It's just enough to say that the question is very open and active and very interesting for all theoreticians. I have a few minutes to talk about GRBs very quickly, because as we will see, it's only non-observations. So of course the question of TV emission from GRB is a very interesting one. It constrains the maximum energy of electrons, the problem of optical depth, and so on. So there is a procedure, a TO procedure following any GRB alert. If the GRB is visible in the field during the night, the Hess telescope is pointing very quickly, maybe not as quickly as magic, but in a few minutes towards the GRB. And it's observed during 1 hour, waiting for further information. And if the GRB is interesting, not too far, and of course still visible, follow-up observation are carried out the following nights. So in one case, per chance, there was a GRB detected in the field of view during an observation. So it's extremely rare, but it can happen. So in the 5-degree field of view, Hess was observing an object, and the GRB happened just in the field of view. So in this case, we have observation before, during, and after the GRB. But unfortunately, or because it's unfortunate, because it can bring information, but you see no excess of gamma ray photons, that's random gamma ray detections, and the GRB happened here, and there was no excess during the burst. And it puts some upper limits, of course, on the GRB. So the GRB itself could be unusual because it was a very soft spectrum, so it could be due to a galactic burster, but it was not identified and there is no redshift information. So an extragalactic origin is not excluded, but maybe. So that's the list of all GRB observations carried out with good quality runs. They are all brought upper limits with good detection. There were 22 good runs after a good run selection, 2 shorts and 20 longs, 10 redshift determination. On this 10 redshift, 6 were below 1, and the minimum value was rather close, so it could be observable with, even with extragalactic light attenuation, and no detection, as you see. the histogram of significance is compatible with 0. So in conclusion, Hess is still providing active and providing new VHA sources, and some of them appear next year, like the stereoscopy is very valuable to bring improvement for expanded objects and for fake objects. There is a great benefit, of course, from all multi-wavelengths and collaborating different ACP campaigns. And the high sensitivity data are very concerning for the model, especially for lasers. So, but of course, it's more and more difficult to do to filter objects because of analog effect. And as I said, the aging of the infrastructure is somewhat a concern up to now. So we are all waiting for S2, which is the next phase that should start next year, hopefully. And thank you for your attention.
A few questions. Yes, three.
Can you explain the problem that you sort of skipped of the statistics of the lasers and the...
Oh yeah, because I didn't put it on the transformer. But I have published something underneath it, so just if you take the number of detected lasers, it's a fair fraction of the if you take all the closest non-BLX, well, there is a unification model between BLX and radio galaxies. But if you take the number of BLX compared to the number of radio galaxies, you have much smaller Lorentz. The Lorentz factor deduced from this unification model are much lower than the one deduced from the TV emission. It's not 50. It's more between, following the wavelength range, between 3, 5, maximum 10. And so the number, the opening angle is larger than the 1/gamma deduced from very.
But if you look at the superluminal motion, the BLX is actually low speed. So
Yeah.
what do you, the statistic you do the radio observation. And this is perfectly consistent.
No,
Just think that
I think the absence of superluminal motion is another problem. Because right, the TV lasers are, they are very rarely having superluminal motion. Most of them, they don't have superluminal motion.
That's consistent with what
No,
you said.
it's consistent with the fact that the jet is pointing at small angle, of course.
No, it's also consistent with the idea that the Doppler factors associated with the jets are more like 3, 5, maybe 7.
Yeah,
No,
but it's not consistent with the TV observations.
So
Because the relative models, they imply much higher Lorentz factor.
They're not consistent with the TV models. They're not consistent with TV observations.
Yeah, I agree, but that's just the absorption of TV photons. So there is a problem between the Doppler factor deduced from relative models and the Doppler factor deduced from
Geometry has a spectrum where the jet decelerates from the TV region to the radio. And that seems like perfectly fine.
No.
You don't like it?
No, because the TV, there should be much less TV. If the TV laser, if the TV emission was very well beamed with 1/gamma angle, that's not the topic of the talk, but you should expect much less BLX in TV. If the TV pattern was much narrower than in the other wavelengths, you should have a tiny fraction. The TV lasers should be a tiny fraction of the overall blazars. Because the opening cone of the blazars with respect to radio galaxy.
Yeah, but maybe that's as simple as that. Maybe
Okay, we can discuss
the TEV code is not so small.
So maybe we should
I
move
think
on
we
to
can
one more
discuss it.
question and then we can.
So it's rather common because I don't think that you can make any statements about this because there is nothing like a TV survey that you can make population studies.
Yeah,
So there is a list in some paper of HBLs and we just observe with Hess.
we have systematically
detect,
observed all the blazars, all the most luminous blazars in X-ray and radio. So we have not detected all of them, but we have detected a fair fraction. And what I say is that the fraction we have detected is much larger than the fraction we should have detected if the Lorentz factor of the TV emission was so high.
We observe all HBLs, and the number of HBLs fits the unification models, and all HBLs are detected, so it's
I
consistent.
think
It may
we
just
have to-
be that the jet opening angles are larger than 1/gamma.
We say that the
That's true.
radio freelance should be
I think that's the right explanation. But,
Okay,
it's not a, it's not a double.
let's thank our speaker. This is by Maxim Barkov, GRB Central Engines as magnetically driven collapsar model.
Hello, thank you for the invitation to this workshop. This work was made with Sergei Komisar and Lips, and I will try to discuss about physics of central engines of JLBs. I will talk only about the central part. I think you know what is JLB, and it's not needed to explain what we observe. We will talk about only very central region. How we can explain such huge energy release during gamma ray bursts? We have several sources. One of them is accretion disk, massive accretion disk. We have a quite short accretion time for compact disks, and if we have a merger of a black hole and neutron star or two neutron stars, this is the best way for explanation of short gamma ray bursts. For long one, more promising is collapsar scenario, when we have a collapse of a massive star with a Fermi core, and we have a growth of a black hole, formation of accretion disk, if we have enough angular momentum, and how we can get the energy from accretion disk. We have several possibilities. One of them is neutrino heating, when we have huge neutrino flux which will hit the plasma near the torus. Another way is magnetic braking of massive accretion disk. And also we can explain the central engine like a fast rotation neutron star with a strong magnetic field, which also produce a relativistic jet, and we have enough energy in rotation and quite efficient transformation of rotation energy to jet. Let's discuss what we should expect for magnetically driven collapsar model when we take into account Blenford-Znayak mechanism. We should satisfy the criteria for explosion which we discussed 1 week ago. And to have an explosion, we should have a very strong magnetic field and very fast rotation. But if we have a strong magnetic field, it stops differential rotation and even stops fast rotation in star. So we could have a somehow conserve of fast rotation if we don't have a magnetic field in the star. But in such case, we almost don't have a chance to make a magnetic explosion. If we form a neutron star, we can expect what fast growth of magnetic field on fast rotation of neutron star will form enough magnetic flux and it will explain the explosion. we could form and generate magnetic field in a torus, accretion torus. And we can easily estimate the value of magnetic field in a torus. It has a quite high value, and it looks enough for formation of gamma ray bursts. But we need a large scale magnetic field, and it reduces the strength of magnetic field on 1 order of magnitude, and it's not enough for explanation of gamma ray burst. You just don't launch it. You will have a just accretion. So, how we can get so strong magnetic field? It could be just seed magnetic field which we collect on a birth of a massive star. And if we have a closed binary system, due to tidal interaction, we can save the fast angular rotation, and we can expect the progenitor for gamma ray bursts. We require very high magnetic flux for explosion, and it's almost on the upper limit of most magnetical massive stars in our galaxy. And we could estimate what in our galaxies is how the stars will have a little bit more magnetic field. It's confirmed by just observation of magnetic field in different galaxies. Usually our galaxy is lower magnetized than nearby galaxies. We can say what this rarefaction due to strong angular momentum could help to start the explosion. Another way, it's just neutrino heating from accretion disk could stop the accretion to polar region, and it also can help to launch the magnetically driven gamma ray bursts. And we show what the diffusion time much longer than lifetime for massive stars. So, what we can expect? We can expect a large-scale magnetic field, closed binary system, and solid body rotation of a star. And it means the best candidates for gamma ray bursts is closed binary system with Wolf-Rayet star. We know at least 3 systems with enough fast rotation and Wolf-Rayet star component and massive stars in a component. We calculate a very simple toy model how to estimate the growth of a black hole and estimate the spin of a black hole. We calculate the accretion in a threefold scale, and we decide, is it angular momentum in this cylinder enough to go to a disk? We will accrete it through disk. If it less, it will accrete it directly to black hole. And we get a very good agreement with numerical simulations on a level of 1%. And what we did? We can see the growth of a star, of black hole, and growth through the direct accretion for different angular momentum distribution, and growth through disk accretion. And here we can see the changing of the spin of a black hole. So we can say what speed of rotation for black hole not so quick, and we don't have a 0.9 something. We have only 0.6, 0.7, 0.4, and we have a very moderate rotation of a black hole. Also, we can say what the mass of a disk not so big. Also, because we have a very condensed to a center density distribution. We make the same calculations for more realistic models for Wolf-Rayet star, and we get the same results and very close results. You can see what we have the value for start of the disk rotation on a region of 0.4, 0.6. And we just put such initial conditions for our model. Also, we can estimate the accretion rate through the disk, and we know what the neutrino limit is quite high, and only several of the models satisfy high neutrino limit for housing. If you have a strong accretion, you have a stronger flux in neutrino, stronger heating. If you don't have enough accretion rate, just neutrino heating not effective. It drops very quickly and very strongly. In this case, Blanford-Znayak limit it's much lower. It's -5. So, what we make in our calculations? We have a massive star with 10 solar masses, moderate speed of rotation, solid body rotation, and big scale magnetic field. We use a better distribution of density and shift our start point on 17 seconds, and we collect some magnetic flux to black hole. We use better work for free-fall model. We have a distribution of the density, accretion rate. We use Kern metric for our calculation. Code is generativistic, MHD. We use realistic equation of state. We take into account the dissociation of the nuclei. We have neutrino cooling, but no neutrino heating in our calculations. What we get? For this is results for different spin of a black hole and for different magnetic flux. We can see what the effectiveness of process quite high. Another interesting point, in one simulation, usually I can say it's near 20 or 15% we have one side jet in our simulations. And we can estimate the kick from one side jet. It's near 200 kilometers per second. Here it's a movie how it happens. We start with our simulations on a point of a disk formation. We have some corona around the accretion disk and launch of a jet, and occasionally it starts on one side. And in this moment we have accretion from another side, and the matter comes to equatorial plane, don't meet another flux from another side, and come to another pole and lock the launch of a jet from another side, and it looks quite stable situation. So, usually we have two side jets, but on 80%. Here it's plotted the distribution of the density, vectors, arrows, it's velocity distribution, and lines, it's magnetic field line. And here we see in a central, we see? No? In a central region we have accretion, and on the outer region we have acceleration by magnetic field. And conclusions. We can say what magnetically driven gamma ray burst could have place, but they have a strong restriction for this model. We should have a very strong magnetic field and we should have a fast rotation. Common envelope would help to get extra angular momentum to envelope. And we can say it's a very good model to explain very long gamma ray bursts. When you just don't have enough accretion rate for support the neutrino cooling, neutrino heating mechanism. And thank you for your attention.
Thank you very much. Now for questions, yes?
You have put some slide where you say basically that the extraction of energy from the accretion disk with magnetic torques is basically ruled out according to your estimates. But we have done numerical simulations of magnetic-rotational core collapse using the same flux to the equator, roughly the same as you have using for the Blanford magic effect, and we get such outflows prior to the formation of the black hole. So this is a key difference because you are, I don't know how you are doing this estimate, whether you have already the black hole core or it's still collapsing the star or what, because it's fundamental that if you produce the jet a little bit before, say, so to speak, you create the black hole, this helps a lot. You already overcome the run pressure of the collapse, and then later a little bit of extra winding can help you to develop the alpha.
How to say, you could get formation like a neutron star in the beginning, and for more massive models, you will have just formation of a black hole without jet and so on. And it's a big difference in the angular momentum distribution. How you have it in the very beginning. If you have a solid body rotation, you don't have no disk, nothing. You just accrete to a central object which will collapse to a black hole. If you put some extra angular momentum to a center, you could get accretion disk, neutron star with support of centrifugal forces. But if you have magnetic field and fast rotation, it should be like a solid body. And I think what you will get black hole first and after disk and so on.
Another question, Andrew?
Yeah, so for your plots of black hole rotation, why did you start at 0? So shouldn't the black hole be rotating when it's born? And then if you accrete onto it, it will grow faster.
It's a question of for solid body rotation,
Yes.
and your black hole formed from a ferrum core, which compact, quite compact. And during collapse, it initially have almost 0 angular momentum. And in this reason, we start from a 0 point. And how to say, the matter which accreted from a pole region slow down quite effectively the black hole. And it looks reasonable, our estimation, coincide with formation of a black hole, which you can find of seconds of papers, Shibata and Shapira.
So that's because the core forms mainly from the matter that falls along the rotation axis?
Yes, before accretion disk formation.
And also because you're assuming solid body rotation.
Yes, solid body rotation.
Yeah. Did you just for fun try a bigger curve parameter? So your 0.6 and 0.4 are relatively inefficient compared to
how to say, we play with different spin parameters. For low mass black holes from 0.9, 0.5, 0, and how to say, calculate the mesh of models. And our results have agreement with the Blanford-Znag formula on a level of 20%. It's almost you can estimate it immediately what you will get. Estimate the magnetic flux on a black hole, mass, it's all. You get the result.
Okay, well, we should thank the speaker. Thank you.